All right, let's jump right into this explainer. We are diving into the absolutely fascinating world of how mathematical models can actually help us predict the chaos of space missions. Because, look, when you're designing hardware to survive the brutal environment of the cosmos, you can't just guess what's going to happen, right? You really have to map out the possibilities. And to pull that off, you need the right mathematical tools in your belt.
But before we even think about looking at a single mathematical formula today, there is a foundational, detective-style question you absolutely must ask yourself. And it's this: what variable am I actually measuring and what physical process generated it? If you're just picking a formula because the shape on a graph looks nice, you are flying completely blind. Truly understanding the physical reality behind your data, that is always step one.
And our baseline tool for answering that is a probability distribution. You can think of it as a predictive map of potential futures, all based on the data you've gathered. Basically, it just describes the possible values of a variable and tells you exactly how likely each of those specific values is to actually happen.
To help us navigate these models, we've broken this briefing down into 5 key areas. 1. The core of probability. 2. Discrete space events. 3. Continuous space measurements. 4. Modeling time and reliability. And 5. The master distribution toolkit.
Okay, starting off with section 1, the core of probability. So, the crucial takeaway here is that choosing your distribution depends heavily on whether your data is discrete or continuous. It's a huge distinction. Discrete data means you're counting chunky, distinct events. You can't really have half of a satellite failure. Continuous data, on the other hand, means you're measuring smooth variables. We're talking things like time, distance, or temperature, stuff that can technically be broken down infinitely. Moving right along to section 2, discrete space events.
Enter the Bernoulli distribution. This is our absolute simplest building block. It describes a single experiment with only 2 possible outcomes. It is strictly binary. We're talking success or failure, working or failed, detected or not. Just imagine a ground station trying to pick up a single data packet from a satellite. It either successfully gets it or it doesn't, no in between.
But what's really fascinating is how the binomial distribution takes that simple yes or no Bernoulli event and scales it way up into multiple independent trials. So instead of just looking at one isolated event, it counts the total number of successes across a fixed number of attempts.
Let's put that into a practical space context. Say your satellite is transmitting 20 separate data packets. If every single one of those independent packets has a constant 90% probability of success, the binomial distribution can calculate the exact odds of exactly 18 packets making it safely to the ground. You want to pull this tool out whenever you've got a fixed number of trials, 2 outcomes per trial, a constant probability, and completely independent events.
Okay, but what if you aren't counting a fixed number of trials? What if you're tracking random independent events over a set block of time? Like, say, counting an average of 2 single-event radiation upsets on a spacecraft per month. Well, that's where the Poisson distribution comes in. It describes how many times an event pops up during that fixed interval, assuming they're happening at a roughly constant average rate.
Let's shift gears to section 3, continuous space measurements.
Now, these 2 universes, discrete and continuous, are actually super closely connected. While the discrete Poisson distribution counts the chunky number of events occurring, the continuous exponential distribution measures the smooth waiting time until the very next event hits. It's really just 2 different ways of looking at the exact same cosmic phenomena.
Then again, sometimes we don't have a neat cluster of events at all. Sometimes we have a uniform distribution. That just means every single value within a specified range is equally likely to happen. For instance, if a signal's arrival time is equally likely to hit anywhere within a known 10-second window, we use a uniform distribution to model it. Why? Simply because we have absolutely no logical reason to consider one specific millisecond more likely than any other.
And then, of course, there's the undisputed heavyweight champion of continuous data, the normal or Gaussian distribution. Whenever you have measurement errors influenced by a ton of tiny, independent sources, like repeated GNSS position errors, we use this classic symmetric bell curve, where values predictably cluster right around the mean. You'll notice 68% of values fall within 1 standard deviation, and that jumps to a massive 99.7% within 3 standard deviations. But hey, a quick word of caution, not all errors are normal, especially if your data has systematic biases or crazy massive outliers.
All right, on to section 4, modeling time and reliability.
Let's circle back to that exponential distribution we mentioned a minute ago. The most crucial, kind of mind-bending thing about the exponential distribution is this highly counterintuitive idea: it is entirely memoryless. Mathematically, this model assumes components simply do not age. It assumes a failure doesn't depend at all on how long a part has already been ticking away in space.
But, as literally any aerospace engineer will tell you, physical hardware absolutely does degrade. Because spacecraft suffer from real-world aging and wear, engineers rely on the Weibull distribution as a much more realistic fix for that whole memoryless assumption. The Weibull distribution actually allows the failure rate to change over time.
And it is incredibly versatile. Just by tweaking a shape parameter, you can model totally different physical realities. If the shape is less than 1, you're modeling early life or manufacturing defects. A shape exactly equal to 1 flattens it out into a constant failure rate, acting exactly like our memoryless exponential model. And a shape greater than 1? That beautifully captures the inevitable wear-out failures that become way more likely as things age, like degrading reaction wheels or dying batteries.
And finally, Section 5, the Master Distribution Toolkit.
So this right here is your ultimate cheat sheet, perfectly summarizing everything we've pulled from the source material today. You can trace every single distribution, Bernoulli, binomial, Poisson, uniform, normal, exponential, and Weibull, right alongside its specific data type. But honestly, the most valuable part is the main question column. That tells you exactly when to deploy which model based on the core question you're trying to answer, complete with a practical space example for some real-world context.
But ultimately, navigating these models and actually predicting success in the cosmos doesn't start with just recognizing a mathematical shape. You can memorize that cheat sheet all day long, but if you want to truly master this stuff, it all starts and ends by asking yourself that one fundamental question. What variable am I measuring, and what physical process generated it? Because if you can anchor your math to the actual physical reality of your mission, you can predict just about anything. But it definitely makes you wonder, what crucial physical processes are you currently ignoring in your own data? And what unseen disaster might that mathematical blind spot be silently counting down to? Thanks for joining me on this explainer. I'll see you next time.